Hey, so in this video I wanted to show you how to read the gyroscope and accelerometer data off this IMU sensor made by STM32. So it's the LSM6DSOX IMU, and I'll be using a Raspberry Pi to do this. So as you can see on my screen, we have the gyroscope data in the X, Y, and Z, and also the accelerometer data in the X, Y, and Z. And then also here's the SPI transaction receiving the raw data. And then in the C program, I'm converting it into physical units so that it can be used in any project that you want. So yeah, let's get to it. So to get started, let's open up VS Code, new empty window, and then let's click on here. Well, before we do that, if you haven't already, install the Raspberry Pi Pico, extension. This will basically install everything you need to compile a Raspberry Pi Pico project. So once you do that, you'll get these extra buttons on VS Code, and click on this one. Let's go new project. I'm going to name the project IMU. And then I will be using the Raspberry Pi Pico 2 for this tutorial, but you can use any of these, it should all work. And let's save this project somewhere. And as far as features, all we need is SPI and then console over USB so that we can print to the serial terminal, and the rest we can leave as is. So let's create. All right, so now we have an empty project, and let's go to the C file, and it's going to have this boiler code, and let's just delete it all for now. And then I'll copy and paste the code that we need and explain it as we go. So the first thing you'll want to do is include your libraries. stdio is used for input-output functions like printf. Then we have the Pico standard library, which has essential functions for setting up USB and UART for printf, and it also has delay and GPIO control functions. And lastly, we have the hardware SPI library, which provides functions to communicate via UART. All right, now let's include our main function. stdio init_all will allow us to use printf to print over UART and USB. And then we have the while loop, which will contain a function for reading the IMU data, so the accelerometer and gyroscope data off the IMU. So here's the pinout diagram of the Raspberry Pi Pico 2 and also 1. And it has two SPI cores, so it has SPI 0, as you can see right here, and it has SPI 1. And you only can use one at a time, so we are going to use the SPI 0 core, which is right here. So we'll be using GPIO pin 16, 17, 18, and 19. And then on the actual IMU chip, we'll be using VN, ground, SPI clock, serial data, data out, and chip select. So as mentioned, we have our MISO, which is master in slave out line, which is GPIO pin 16. So you can see that right here. So the RX stands for receive, so that's why it's master in. We have our chip select N, so this is an active low chip select line, which is pin 17 on the Pico. And then we have our SPI clock, which is pin 18. And then we have our MOSI, which is master out slave in pin 19, and that is this SPI transmit for TX. So in addition to the lines, we need to add the identifier that's going to allow us to use the SPI 0 hardware. So that'll just be this line. The next thing we need to determine is the clock frequency for the SPI. So that can be found in the datasheet on page 13. And as we see in this table, the clock frequency can be 10 megahertz. So that's its max frequency. And it says that values are guaranteed at 10 megahertz, so that's good. So let's add that to our code. The next thing we'll want to do is write the function that'll set up all the GPIO pins to use their SPI functionality. SPI init core is a wrapper function that contains functions from the stdlib and the hardware SPI library. Its arguments are the SPI instance and all the GPIO pins we defined up here. First, we'll initialize the SPI by setting the SPI instance and also setting the clock frequency. And then we will set the GPIO function to use its SPI functionality. So what that means is instead of using the GPIO pins as regular GPIO pins, we'll use their SPI functionality. So each pin is assigned SPI functionality, as you can see right here. Next we have SPI set format. So this takes in the SPI instance, the data bits, which will be 8 in our case, the clock polarity and the clock phase. And then lastly, we need to tell the SPI which bit we'll send first. So in this case, we'll be sending the most significant bit first. So by looking at the register map, we see that the data contained is 8 bits. So that's how I know that the data size is 8. And then also, when we look at the communication interface characteristics, it gives us a nice diagram in mode 3. And that's how I know we should set this to mode 3. Also, we can determine that the most significant bit should be sent first by going to section 5, so digital interfaces, and then SPI. And if we scroll down to the SPI section, we see the data bits right here, and as you can see, bit 7 is sent first, and that tells us that the most significant bit is sent first. And lastly, we initialize the GPIO pin for our chip select pin. This may be a little redundant because we're already setting it up here. So maybe on your end, you can try to update this function without this call, and it should still work. Next, we must set the direction of the chip select pin, so this will be output. And then we want to set its initial state to high. As you can see in this diagram, when the SPI interface is idle, the chip select line is high. And that's what we're doing right here. So the next thing we'll want to do is to write the functions to read and write to the sensor, to and from the sensor. So by reading through this documentation, we see that when this bit, the read-write bit, is 1, that means we're going to read. So with that in mind, let's look at this first function right here, which is to read a register. The arguments for this function will be the SPI instance, it'll be the chip select line, the register that we want to read from, the buffer which will contain the data at that register, and also the number of bytes we want to read. So how this function works is first we check to see if the number of bytes we want to read is at least 1. So if it's less than 1, then we return because we can't read like nothing, basically. So here we are ORing the register value with the value 8 because we want to tell the IMU that we want to initiate a read from one of its registers. So by looking at this waveform, we can see that the first thing we need to do is write the address to the IMU. And the most significant bit of this first 8-bit transaction has to be high in order to initialize a read. So for example, say the address we want to read from is, let's see, 1, 2, 3, 4, 5, 6, 7, 8 is address 1. So we wouldn't send this as the address in order to read. We would have to set this most significant bit high, and then when we initialize that transaction, then it's going to tell the sensor that we want to read whatever data is at this address. This block of code is where we do the full read transaction. So if we scroll down a little bit to this next diagram, figure 9, let me zoom in, we see initially the chip select line is high, which is set in the init function right here. And then to begin the read transaction, we bring the chip select line low first, as seen right here. Next, we use the SPI Write blocking function, which is a part of this hardware SPI library. And this takes in the SPI instance, so SPI 0, the register we want to read from. And next, we are reading 1 byte of data. Or you could think of it as one set of this. So we set up the SPI transaction to send and receive 8 bits of data. So that's why this is set to 1, which means 1 byte, which is equal to 8 bits. This entire function can be seen visually on the diagram right here. So we have the address bits as well as the read bit set to high or 1. Next, we use the SPI Read blocking function, which is also from the SPI hardware library. And it takes in the SPI instance, so SPI 0, the repeated TX data, and then it takes in a buffer, so the buffer will contain the data read from this register, and then also the number of bytes you want to read. So if this is set to 1, it'll read the data at this register. If it's set to anything more than 1, 1, then it will do a burst read. So the first data read from will be from this register, and then the next data will be read from the next register. Lastly, once we have read the data back, so right here, we bring the chip select line from 0 to 1, and that is what we are doing in this line right here. And then this function concludes by returning the number of bytes read during the SPI read transaction. So if we scroll down a little bit, we see the write protocol right here. So we'll be implementing this in code. So let's look at this code right here. So this function is pretty similar as far as the arguments as the read. So we take in the SPI hardware instance, the chip select line, the register we want to write to, and also the data that we are going to write to that register location. So the message, or the write message, will contain 2 elements. The first element will be the register that we want to write to. So similar to reading, if we want to write to, say, address 1, instead of this most significant bit being high, as you can see, the write has a bar on it. So that means that most significant bit needs to be 0 to indicate a write transaction. So then, for example, this would be 0. So that's why we are ANDing the reg value with 7 and F, because the most significant bit of this value is 0. And then the next element in this message array will be the data, to which we are going to write to whatever address that this points to. So again, just like the read transaction, initially the chip select line is high, as you can see, so we have to bring it low first. And then we start our SPI write transaction, so that's what this function does. So it takes in the SPI hardware inst, the message that we want to transmit, and then also the number of bytes. So usually we're writing, 1 byte to a specific config register. So this function is sort of hard-coded to basically write 1 byte to a register. There's 2 right here because remember we're transmitting 2 bytes, the address and also the data, but only the data will be written to this address. And then lastly, to complete the SPI transaction, we need to bring the chip select line from low to high. So that's what this is doing. It's bringing it back up to high to its idle state. Now let's take a look at the register map, and there's only, 4 registers that we need to consider. The first register is who am I, and this basically contains a hard-coded ID value. So this is 6C, and this is a great register to start off with. And what you're going to do is just try to read this value back. And by reading this value back, it basically confirms that your read function up here is working properly. So the next register we need to consider is this control1XL register. So this allows us to configure the accelerometer, and then control2_G allows us to configure the gyroscope. And then lastly, we will be looking at control3C, and this lets us configure some general settings for the IMU, like doing burst reads, for example, which will be important for this tutorial. So let's copy these addresses. So as you can see, the address for each register is right here, so given in hex and then in binary. So let's use the hex value because it's a little easier to work with. Let's copy those right here. So let's write this IMU init function. And the first thing that it does is that it tries to read the who am I register. So here's the who am I register, and as you can see, it contains a fixed value of 6C. So what we're going to do is let's delete all this, and let's just try to read the who am I register in the while loop. And by doing this, then it confirms that our read function works, and this is a very good step for like debugging. And then we can sleep for 1,000 milliseconds, which is 1 second. All right, so let's connect the Pico to the breadboard, and then let's get our IMU and connect it right here. Let's connect ground first, so pin 38 to the ground pin right here. We can see that this pin right here is 39, so the one right below it is ground. and then we have ground right there. The next thing we can do is power. So power is pin 36, and then that'll connect to the VIN. So 36 is right here, and then power is right there. Now let's connect our TX. So that'll be connected to our serial data. So the TX is transmitting data out, and that'll go into the serial data line. So TX is pin 25. Which is right there, and then our serial data is right here. Next will be our SPI clock. So pin 24 goes to the SCL. Pin 24 goes to SCL. Then we have our chip select line. Pin 22 goes to CS. So pin 22 goes to CS. And lastly, we have our SPI RX, which will go to serial data out. So data coming out of the sensor and then into the Pico. So that's the pin 21, and that goes to DO, data out. Okay, cool. So it looks like we have everything connected, and I'll also connect my Logic Analyzer so that we can see the transaction going from the Pico to the IMU. All right, so let's compile the project. So let's go over here, and then let's click on Compile Project, and everything looks good. Let's open up a new bash terminal, and then let's cd into our build folder. And then the file that we're interested in is this .uf2 file. So this is the binary that we are going to flash onto the Pico, and it'll run our program. So now we want to flash our program onto the Raspberry Pi Pico. And in order to do that, we need to hold down this boot select button and then plug in the micro USB and then let go. And as you can see, it mounts as like a drive. And then what we can do is copy this UF2 file to this drive, and as soon as it copies over, then the Pico will start running that program. So let's do that right now. Okay, so to copy the program to the Pico, let's copy imu.uf2 to media, our username, and then the Pico drive. And then we can press enter. Okay. So now let's go to the terminal. And if you haven't already, or if you don't know what it is, you should install this program called Minicom. So sudo apt install Minicom. So what this does is allows us to see the data coming into our computer on the serial terminal. So if we do sudo Minicom and then -d, and then select the device, so TTY should be ACM0, and then we'll select the baud rate. So the baud rate will be 115/200. Press enter. Okay, so nothing's happening, but I think I found my mistake. Let's return the number of bytes. Oh, I see my mistake. Okay, so I forgot to call this function. All right, so let's call that first, because if we don't call that function, then our SPI hardware isn't set up, and then we can't do any SPI transactions. So let's compile the project and then reflash our Pico. And there we go. So now we're reading the Who Am I register, and let's look at the SPI transaction. So this thing is getting a little corrupt because my Logic Analyzer isn't that great. So that's why we can see the data changing a little bit. So let me fix this by slowing down the SPI clock. Let's go here, and let's make this 400 kilohertz. Recompile, reflash the Pico. Looks like it's working again. So as you can see, we're doing a read transaction. So first, the most significant bit is high, and then we send the address. So this is 0 right here, and then this is the 1s for the F right here. And then next, we're reading back 6 and C. So it looks pretty good so far. So the next thing we'll want to do is configure the accelerometer control register. So here we can see the field of each bit inside this register, and here's the description for each bit as well. So for the accelerometer high resolution select, I usually leave this as default, which is 0. So next we can look at the full scale, and the full scale is at this table down here, and it basically tells us what range of G's we'll be able to read from our accelerometer. So for example, if we pick 8, then we'll be able to read positive 8 Gs and negative, all the way down to negative 8 Gs. So let's pick that. So then this will be 0 because that's reserved. And then this will be 0 because we're selecting the default. And then we'll have 1, 1 for 8 Gs plus or minus. And then for the output data rate, we can come down to this table and pick how fast our output data rate will be. So that's what ODR means, output data rate. Let's say we want to read the sensor at 1 kilohertz, so then we can select 1.66 kilohertz as our output data rate. Okay, so we have 0, 0, 0, 0, and then 1, 1 for the full scale, and then we have binary 8 for the output data rate right here. The next thing we'll want to do is configure the gyroscope control register too. So it has a similar layout as the accelerometer register. So the first bit is reserved, the next bits are for the full scale, and then the next bits over here are for the output data rate. So for this full scale 125, I leave at the default. And then for the full scale UI chain full scale selection, let's say we want to read a range from positive 1000 to negative 1000 degrees per second. So then we'll put 1, 0 or 2, so right here, so 0 and then 1. And then let's read at the same output data rate as the accelerometer. So that'll be right here. So this will be binary 8. So it'll be 0, 0, 0, 1. And that's what we have here. So we have the 2 zeros for here. We have the 0, 1 from here, which is this. And then we have the 8, which is right here. And that's right here. So the last thing we want to consider is this control register 3. And we want to leave everything as default except for this IF Inc register. And by setting it to 1, it allows us to do incremental burst reads, which is good. Because all of the gyroscope and accelerometer registers are adjacent to each other, we can do a single burst read and get all the raw gyroscope and accelerometer data in one transaction. So let's put that right here. Yeah, that's pretty much it for initializing our IMU. Okay, so using the same structure right here, let's reflash our Raspberry Pi Pico so we can see the transaction. So as you see, we are printing out the data, and that matches what we see in our code. So who am I is C6, as we saw in the datasheet. For control 1 Excel register, we wrote 8C, so that's what we see right here. And then for the control 2G register, we wrote 88, so that's what we see right here. And then for the control 3C register, we wrote 4, which is what we see right here. And if we look at the transaction on the Logic Analyzer, we can see the same thing. So the who am I register is 0F, but we see 8F because we're reading that register. And here's the C6C that we get over here. And then for the other configuration registers, first we are writing and then we're reading back. So the next register is at location 10, and this read-write bit right here is set to 0 because we're writing. And then we are writing 8C to that location, and then we're also reading it back. And then you can see that this is now a 9 because this most significant bit in the address for reading is now set to high. And that's how we get that 9. But it's still address 10. Hopefully that makes sense. And then similarly, the next address is at 11. Here's the address at 11, we're writing 88, and then we are reading 88 back, and again, the read bit up here is set to high because we're reading. And then the next address is at 11, and we're writing 4, and then we are reading back at the same location, and we get back a 4, as seen right there. So everything right now looks pretty good. Okay, so let's move this function out of the while loop, and then let's write the main function for reading the gyroscope and accelerometer data. So let's return to the register map and look for something that looks like it could be gyroscope and accelerometer data. And that is right here, this OutXLG, and then this OutXHG all the way down to the A's, which is accelerometer. We got the X, Y, and Z for the accelerometer, and the X, Y, and Z for the gyroscope. So the way the data is stored in the IMU is that there's an LSB byte and then there's a MSB byte. And if we go to the description of those registers in the datasheet, we can see that the angular rate sensor pitch x-axis is expressed as a 16-bit word in 2's complement. So basically what that means is that we have to combine the lower byte and the upper byte and form a 16-bit value, and then read that as an integer in our code. So I'll show you how to do that right now. Okay, so let's add this single register to our code. And remember, we only need this one value because we're going to burst read all the others in one SPI transaction. Now let's add the main function for reading the data from the sensor, and let's also add some global variables. So first we're going to declare this variable num_bytes_read and initialize it to 0. This is actually optional. I won't use it in our code, but this will be nice for error handling if you plan to make your code more robust later. So the next thing we want to do is read 12 bytes into our raw buffer. So if we come up to our variable declaration up here, we see that we have a uint8 array of 12 elements. So that's because we want to read all 12 registers, so from 22 all the way to D2 in one SPI transaction, and store each output data into one buffer array. And we are able to do a burst read because of what we set at this register. So setting this bit to 1 right here allows us to do a burst SPI read transaction. Okay, so the only thing we're going to view is the raw data on the serial terminal and also on the logic analyzer. So let's call this function in our while loop, and then let's compile and then flash the new program onto our Pico. Okay, so as you can see, we have the raw data being printed to the serial terminal, and then if we look at our SPI transaction, we can actually map what we're seeing on the transaction to what's being printed out. So if I take a single shot and then unplug my Pico to stop everything, let's see if we can find this transaction on the serial terminal. So actually it's found right here. So that's F7, F7, FF, FF, and then we have 4, 0, 7, 0, AC, 0, 6B, FF, 48, and then 10. So that looks perfect. And then as you can see, we are doing a burst read. So the first data is found at address 22, but since we are doing a read transaction, we set this first bit high, so then it looks like an A2. Hopefully that makes sense. And then we do a burst read of 12 bytes. So this is the LSB byte for the X gyroscope, and then we have the MSB byte for the X gyroscope, and then gyroscope LSBY, gyroscope MSBY, gyroscope LSBZ, gyroscope MSBZ, and then accelerometer LSBX, and then accelerometer MSBX, accelerometer LSBY, accelerometer MSBY, accelerometer LSBZ, and then accelerometer MSB Z. Hopefully I didn't make a mistake, and hopefully you understood what I was trying to do there. Okay, so the next thing we want to do is create our 16-bit 2's complement value for the gyroscope and the accelerometer data. So in the buffer, we have the LSB and the MSB for the X direction. And what we can do is OR the LSB with the MSB byte, but then we shift the byte over by 8 and then typecast it into a 16 int type. And that'll be stored in this array, which is type int 16, as we can see right here. So I have one for the gyroscope and one for the accelerometer. And we keep doing that for each direction for the gyroscope and for the accelerometer. So we have the X, Y, Z, or roll, pitch, and yaw. And then for the acceleration, we have the X, Y, and Z. So this data is not usable yet. What we have to do is convert this raw data into a physical unit. So in order to convert the raw data into physical units, we need to do a little multiplication and division. So when we read the raw data from the sensor, we get it in a unit called LSB. And then we need to multiply it by this factor, which can be found in this mechanical characteristics table. And the units of this factor is milladegrees per second. So that can be found right here, milladegrees per second. So when we multiply this with this, the LSBs cancel out and we are left with milladegrees per second. And then to get just degrees per second, we just divide by 1,000. So that's what I'm doing right here for each direction. So we have the X, or the roll, we have the pitch, or the Y, and then we have the yaw, or the Z, for our rotation from the gyroscope. And then similarly for the accelerometer, we chose plus or minus 8 as our full scale. So we have to multiply it by 0.244. And that value has units milli g-forces over LSB. So the raw data from the accelerometer is LSB, and then we multiply it by this value, or this unit, and we're left with milli g-forces. So then in order to get g's, remember g's is, so 1 g equals 9.8 meters per second squared. And in order to get g's, we need to divide millig's by 1,000, and then we get our g's. Oh, and let me clarify. So 1 g equals Earth's gravitational force, which is 9.8 meters per second squared. And by doing this conversion, we get our float values. So let's go up here, and I have a float array declared for both the gyroscope and the accelerometer. And this is basically the last step you need to do to get the gyroscope and accelerometer data from the IMU. So let's comment this, and then uncomment this print line, compile, reflash the board by putting it into boot mode, and then copying over the file. So now we have the gyroscope data in degrees per second. So this should all be 0 because the accelerometer is laying flat on the table. So as you can see, when I tilt it, the values change a little bit. And then for the accelerometer data, we have 0 for the X and Y, and then we have 1 for the Z because we are always getting 1 g of downward gravitational force on the sensor. So one thing we can do is we can look at the diagram right here and change the orientation of the sensor, and we can apply Earth's gravitational force on different axes. So if I turn it this way, now we can see that the Y is almost 1, and then the X and the Z are basically 0. And then if I make X point up, now we can see the X go to 1, and then the Y and Z stay at 0. So in order to make sense of the gyroscope data, we know that Z is pointing up. So if we use the right hand rule, rotating the board in this direction, so counterclockwise will give us a positive rotational speed. So let's try that. So let's look at the Z right here, and I'm going to rotate it, and we get positive, and then the other way is negative. So similarly in the Y, which is pointing this way, if we rotate it this way, then that'll be a positive Y rotation. So let's look at the Y. So if I rotate it this way, we get a positive angular rate, and if I rotate it back the other way, we get a negative angular rate. And then similarly with the X, which is pointed this way, if I rotate the board in this direction, we'll get a positive angular rate on the X, as you can see, and then we'll get a negative angular rate going this way. And that's pretty much how it all works. You can shake it to see the accelerometer change in the different directions. Another cool thing you can do is you can measure the exact angle that the board is oriented in, and I'll make a separate video to go over that. So that's all I have for today, and I'll link the GitHub in the description, and feel free to leave comments if you have any questions. And yeah, that's all I have for today. Thank you.